Okay, so I think we can start our for this week. So welcome to the live session for week 7 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. And I am Anant Singhal, a PhD student from IIT Jodhpur, and today I'll be assisting in solving some of the assignment problems that have been given to you in your week 7 assignments. Uh, and that will help you gain more clarity and some of the concepts that we'll be covering. So this is the course outline. Till now, we have already covered most of the important devices that we need to understand in this particular course. We have also covered the p-in junction. We have covered the very basics of BJT. Then in the last lecture, we started with not the FET exactly, but with the MOS capacitor, which is you can say the basic version of a MOSFET. So we studied about how the actual CV characteristics of a MOSFET looks like, sorry, of a MOS capacitor looks like. And we did not talk about high and low frequency CV characteristics, so we can cover that particular topic in this particular lecture also. And then we will quickly see some of the what is a actual or the very basic difference between a MOS capacitor and a MOS FET. So it's just the addition of the drain and source terminal that I will be explaining. And in this particular week, you will see that we have now arrived to the actual modeling part of the course. Till now, we were more or less discussing about the physics of the devices, but now particular all the particular lectures are now more or less based upon the derivations and all of those different theories and different models that we have. So in this week, we'll be covering or we'll be seeing some of the semi-classical transport theory, that what exactly is semi-classical. Then distribution function, this kind of we have already covered in the week 3 assignment, in which I told about the Fermi Dirac distribution function. So this is the same thing. So we'll take a quick overview again. Then some of the Boltzmann transport function, RTA, and scattering and mobility. So we'll be discussing these topics also in this particular week. Uh, Apart from this basic coverage of the MOS field effect transistor. So yeah, so in the previous week, as I have already mentioned, that we have covered the important topic of MOS gap, which is nothing but a MOS capacitor, in which we studied about the different regions that once we apply a negative gate bias, it goes to accumulation. Then from accumulation, then we apply more bias, then it goes to depletion, and at the last, goes to inversion. So this is the basic that we covered in the previous lecture, that this is how actually a MOS capacitor works. We start with applying some negative gate voltage, due to which there will be some accumulation of holes. Once we start to increase the voltage towards positive side, there will be a depletion region of minority carriers that actually gives rise to one more capacitance in series, due to which the capacitance decreases. And in the inversion again, we have a very thin layer of the inverted ions, or the when the minority carriers become equals to the majority carriers in the bulk. So that's when we hit the inversion, and at that voltage, which we call as the threshold voltage. So these all the things we already covered in the lecture, and this threshold voltage we defined. We start with the depletion, that is the flat band, sorry, the accumulation, which is the flat band voltage, which was 5 ms for ideal case, and it was 5 ms minus qss over cox for non-ideal case, in which we have some of the trapped charges also. Then we apply some depletion voltage, which was given by q depletion over cox, and at last we apply some surface potential, which is equals to 2 phi f for the case when we reach the vt. So this phi f is nothing but 2 phi f, which in which the phi f was, we studied that it was nothing but vt ln na over ni. And this Q depletion we already derived, it was something 2 epsilon s Q Na, and then psi s. This psi s is again 2 phi f. And C ox we already know, this is epsilon ox by T ox. So this is the threshold voltage that we actually covered in the previous lecture, and this is a very important formula. So uh, what I would say is, I think we can do a quick numerical again to just recap the concepts that we covered in the last class, because this is the most important formula or the question that that may come into your exams and all. So just give me a minute. Let me fetch some of the question and you can also solve it. Yeah, okay. So the question that I'll be starting with is, let's say we have a MOS capacitor. So first of all, we have a MOS capacitor in which we have not SiO2, but we have HFO2, which has epsilon of relative epsilon of 25. So if you remember, for silicon oxide it was 3.9, but we are now using HFO2 just to give more clarity. And we have a p-type substrate. The electron affinity of the semiconductor is given, so that you don't need to calculate or remember that. Then we have a Eg, which is given as 1.5 electron volt in the question itself. Then we have epsilon silicon, which is given as 10. Ni, let me give you also, let's say for simplification, I'm giving it as 10 is per 12 per centimeter cube. Then Na I'm giving as 10 per 18 per centimeter cube. And then the metal that we have, it has a metal work function of, for simplicity, let's say 5 electron volt. And the oxide thickness in this question, it's let's say 100 angstrom. And we also have some trapped charges, that was for the non-ideal case, which is this. And it is around 5 into 10 to the power 10 Q. Q is the charge, coulomb per centimeter square. So this Q is nothing but 1.6 times 10 to the power minus 90. So all of this information is given in the question itself. The question is, you need to calculate the VFB. The second point is the depletion width. And the third point is the threshold voltage. Is the question clear to everyone? So the few things that you need to be aware of, there is no SiO2 in this dielectric, it is HFO2. So you need to use the absolute permittivity of HFO2. Then it is a p-type substrate, so it will be N-MOS cap. Then you already have been given the electron affinity and you have to use this Ni value for simplification. You cannot use the standard value, because for simplicity I have given this value. Then the metal work function is also given. Oxide thickness is 100 angstrom, which is also 10 nanometer. Oh, sorry, which is also which is also 10 nanometer. That is correct. Then we have a QSS also. So you need to multiply this Q actually to get the actual QSS. So now the question is, you need to calculate the VFB, the depletion width, and the threshold voltage. Is there any doubt in the question itself? Please let me know if you have any doubts in the question. Okay. So maybe you can try it. You can start it and think how to start to calculate the VFP. Then you can go towards XD and then you can calculate the VTH. So I've given the question like that so that all of these concepts will be covered. So each and every formula is given here in this particular slide. You just need to apply your basics and then you will be able to calculate everything. So these are the formulas and this is the question that I've given. So maybe you can take 1 to 2 minutes and start with the problem and then I'll start. Is this fine? Sorry? Yeah. Okay, so is there any answer as of now? So can someone tell how they have started to calculate the VFB? So it is nothing but phi ms minus qss over cox, right? So you have been given cox because you have been given the oxide thickness. So you can calculate cox from here. Then for phi ms, we have phi m minus phi s. So phi m is given in the question. You need to calculate phi s. Now since this is a p type of semiconductor, if I try to make the band diagram, so this is, let's say, vacuum. So for p type, your Fermi level will be close to the valence band. This is EI, this is EC. So we have already seen that from vacuum to conduction band, this is what? No, from conduction band to vacuum, it is electron affinity, right? And from EC to EI, this is EG by 2, right? This is the band gap by 2. And this EI minus EF is actually your Fermi function, right? This is phi f. So you can calculate phi f, you can calculate EG by 2, you can calculate psi s, and the sum of all these three is actually the work function for semiconductor. So for psi s, what you need to do, you need to do the electron affinity plus Eg by 2 plus your phi f. So you have been given this, you have been given this. Phi f you can calculate using how? VTLN Na over Ni. You have been given Na and Ni both, so phi f can also be calculated. So once you calculate phi f, phi s can also be calculated, and phi ms you know. Now you know everything. So once you know phi ms, QSS is given, Cox you can calculate from here. So you can calculate the VFB. Is the method clear? Is there any doubt? Okay, so let me start to calculate because I think you don't have any answers yet. So yeah, so let's start with psi s. So it's 4 plus, so this is the electron affinity that is given in the question. Yeah, it is this plus Eg by 2, so it is 1.5 by 2, and plus VTL and Na over Ni. So it is 18 and it is 12. Okay, so it's 1.5 by 2 plus VTL and Na over Ni. So this is 0.75, so 4.75 plus 0.026 ln 10 raised power 6, which is nothing but 4.75 plus times 6 times 2.303. So if you calculate this, it is coming out to be 0.359, which will make your size to be 5.109 volts. So from this, you have your phi ms, which was the first term of the VFB formula, which is phi m minus phi s. So phi m is given 5 in the question, and this is 5.109. That means this is 0.0109 volts or electron volts. You can write whatever you want. So now for VFB, we have calculated the first term, which is this. Now we need to calculate QSS over COX, right? So to do that, we have QSS is already given, so let's calculate COX, which is epsilon ox by Tox. So in this, the epsilon ox is of HFO2, which is 25 times 8.85 10 to the power minus 14 in centimeter, and then 100 angstrom, that is 100 into 10 to the power minus 8 centimeter. So if you do it, this is minus 6. Okay, this is minus 6, then minus 8. So your COX is 22. It is coming out to be 2.2125 minus 6. That means microfarad per centimeter square. I hope I have done it correctly. So your VFB is actually now phi ms minus QSS over COX. So So you have everything. So 5 ms we calculated 0. What was that? 109 minus QSS is given in the question. It's 5 into 10 is for 10. 1.6 times 4 minus 19 because it is multiplied by Q. Then it is 2.2125 micro. So once you solve this, this will be a VFB. So can you quickly solve this and let me know what is the answer? So this is minus 9, this is minus 3, 6, 8. So it should be okay. So after calculating, I'm getting the VFB to be minus 0.1126 volts. Is there any doubt in calculation of VFB? So we have done this part. Please let me know quickly if you have any doubts. Okay. So for the second part, now the problem is XD. That is the depletion rate, and the formula for that we already derived in the previous class. It was 2 phi s 2 epsilon s phi s into QNA, which is nothing but 4 phi s EF by QNA. So this is just a direct formula problem. So XD is the depletion rate, so we need to write the silicon part here, which is epsilon silicon I've given 10. Phi if we just calculated it was 0.3, right? 0.359 into Q. N is given 10 for 80. Can anyone quickly calculate and let me know what is this value coming out to be? So this is approximately 2 root 2, I think. Anyone did any calculation? This is coming out to be, I've done it, 2.82 10 to the minus 6. This should be in centimeters, which is 28.2 minus 7 centimeter. Why I'm writing minus 7? Because this is nothing but nanometer. So this is 28.2 nanometer. So this is your second part. Now the main question is the VT calculation. Sorry, this. So now you have XT in your hand, you have VFB in your hand. You just need to calculate the VT. I hope you can do that. So it is VFB plus Q depletion over Cox. You also have Cox now. Q depletion you can easily calculate using Q and XD. XD you have, Na you have, Q you have, plus psi s. Sorry, phi s. And phi s is 2 phi f. Phi f you have. So now you have everything. So can you calculate VT on your own? Yeah. Just quickly do it and let me know what you are getting. Okay. So did anyone calculate Q depletion? So we have Q depletion in our hand. So now your VTH would be VFB that we calculated was 0.11226 plus Q depletion over Cox. Cox we calculated 2.215 micro plus 25. It is 2 into 0.359. This is the final answer for VT. This is minus 1. So VTH will come out to be 0.9 minus 0.1. It should be around 0.8. Okay. So VTH is coming out to be 0.809. So this much voltage is required to turn on your MOSFET or your MOS capacitor. Is this whole question clear? Because if this is clear, that means your concepts are clear for the MOS capacitor. That you can calculate anything because this question actually covered all of the formulas that we covered in the previous class. Oh, sorry, I was on mute. So I was saying that if this question is clear, then that means your concepts are clear and we can solve any problem related to MOSFET because we've used each and every formula that we studied in the previous class to calculate all those things that we had. So is there any doubt in this? Okay. So if not, let's quickly take a look at the CV characteristics of a MOS cap. So in the previous class, we studied about the low frequency characteristics. So I mean, we all know that a capacitor is actually only works when we have some AC voltage applied. So we have never shown that. So let's say we have a constant capacitor or let's say this is the gate voltage that we have applied at the input. So at every gate voltage, what we do to work it like a capacitor, we apply a very small sinusoidal voltage over it. Because capacitor blocks DC, so we need to have some AC voltage in reality, which is what I'm calling a small Vg. And let's say it is sine 2 pi ft, that means the frequency is f. And we know that capacitance is nothing but the change in charge with respect to voltage. So we studied that for a normal capacitor, it was constant, such as epsilon ox by T ox. And we started that this was your CV curve, and let's say you take a parallel plate capacitor, and this was your C ox. And then we studied quickly about the three regions, so I'll not go in very deep. I'll just quickly go through that. So whenever the Vg was less than VFB, so what we saw was we had this metal, we had this oxide, and we had the accumulation of holes near the surface, which was nothing but a negative to positive capacitor with a width of Tox. That means we had, so in reality, what we were applying to this was some AC voltage, which was Vg sine 2 pi ft, and then the DC voltage, which was the Vg that we are referring here. So from this, what we were getting out, the CV capacitance. So whenever your CV was still VFB, we were having the constant capacitance of Cox. And then what we did is we increased the Vg greater than VFB, but the Vg we still have kept less than VTH. That means your Vg is less than VTH but greater than VFB. In this, what happened? This was called the depletion region. In this, was what happened? Can someone quickly tell? Let's say this is the metal. We applied some positive voltage here. So let's say still we have that sign. So this was the oxide that had Tox. And once we apply some positive voltage, what we had is we had some depletion region created, right? Which is what we are calling as XD, which was full of minority dopants. So in this, we came to know that this is a separate capacitance, this is a separate. So it is a series combination of Cox and C depletion. And the equivalent capacitance was Cox, sorry. So that means there is a decrease in the capacitance. So yeah, so till VTH, what did we have? We had some decrease in the capacitance, which is something like this. So this is your depletion, and the previous region was accumulation. Yeah, yeah. So for the accumulation, what I was saying is when you apply a negative gate bias, then we have negative ions. And since the majority, this is a p-type substrate, so the majority are already holes. So we had a lot of holes which were present at the surface, which is nothing like a positive sheet plate, right? So this is a capacitance in which we had, sorry, oxide in between, which is having a thickness of Tox and plus minus charge. So it is like a parallel plate capacitor which is having a oxide capacitance of epsilon ox by Tox. So that is why it remains constant till VFB, till it is flat band. And if we apply more and more positive bias, what happens is we have seen that there is a addition of one more series capacitance due to which your capacitance decreases. Yeah. And then at last what we did is we applied even more voltage and we had, let me use some different colors. Yeah, I think this is different. We applied the Vg which was even greater than that of VTH. So whenever we were applying small frequency, that means, okay, let me not talk about frequency as of now. Let's talk about voltage only. So whenever we were applying a Vg, so what we observed is we had actually a sheet of negative ions now because those were the electrons, or I can mark it like small holes. So we had a sheet of electrons. The depletion region was there, yeah, I agree, but the capacitance that we had was this plus minus. So this is like again a parallel plate capacitor which is having Tox difference. So as soon as the VTH reaches, this capacitance goes up again and touches the Cox. So this was your inversion. So this is what we studied in the previous class. Is this clear? I mean, this is what we have already. Yes. Hmm. Hmm. Your- Yeah. So your N actually becomes Na, right? Your minority carriers become equals to the majority carriers in the bulk. So as you have seen here that there was n number of holes, N number of holes at the surface, right? Okay, give me just a second. Yeah. Similarly, it gets inverted and now there are n number of electrons. So it is like again a parallel plate capacitor with positive and negative inverted. So it is again Cox, right? Yeah, because yeah, it again increases. Yeah. So now we need to focus on that these electrons were not present, right? So these electrons have been generated thermally, right? After the application of certain voltage, because we did not have any majority carriers as electrons. So these electrons should have come from somewhere, right? And this electron in general comes from the thermal generation. So now comes the main concept, that is the high frequency characteristics. So let me change the color. Hmm. So in high frequency, what we do is we have the same MOS capacitor. Let's say this is Tox. Oh, sorry, yeah. But in this, what we do is we change the frequency very highly. That is, this frequency is very fast. So what happens? We need to have some response time of the electrons to get them generated, right? So if we increase the frequency too much, then what will happen? These electrons will not get thermally generated because there is no source of getting those electrons generated, because there is no response time because we have applied a higher frequency, right? Are you all able to understand this? Yeah, yeah. So higher frequency mean, yeah, lesser time. That is true. So there will be no generation of. So if you remember till depletion, what we had something like this. And then if the frequency was lower, there was a layer of electrons that was getting accumulated and it was becoming Cox again, right? But what happens at high frequency, these thermal generated carriers does not form. So what do you think will happen if they does not form? Anyone? Mm-hmm. Yeah, exactly. So your high frequency characteristics will look something like this. It will never go up. Yeah. So there is no thermal generation of the electrons because of the high frequency, and your capacitance will never rise up. So if you remember in the last class, I have shown some of the CV problems in which the curve looked something like this yellow one. Now is this clear, the concept? So this is for low frequency and this is for high frequency. Is this clear to everyone? Okay, great. So again, I'll write. So in this, only the first main thing is only the inversion region will change because rest of them will already have sufficient carriers. And then the main thing is the thermal generation of electrons is not fast enough to respond to the high frequency. Yeah. So one more thing is, let's say if we have, so this plot that we made, this was for a N MOS cap. And let's say if we quickly have a P MOS cap, so what will change? Can someone tell? Now we will have an N-type substrate. So what? Anyone? Yes. What will change? Sorry. Hmm. Okay. Anyone else? Yeah, exactly. So now in the PMOS cap, we will require some initial positive voltage so that there will be accumulation of electrons. So this region will be accumulation now. So your VFB will become positive, right? And then we start to apply some negative voltage because we are talking about a PMOS cap here. Sorry. So let me make it more clear. So let's say this is your accumulation. Oops, sorry. Hmm. So let's say this was your VFB now. And in the inversion, what will happen? Sorry, in the depletion, it will again go down as it was the same. Your VT will become negative because we are going from positive to negative now. And for low frequency, it will again rise up and Cox. And for high frequency, it will again. So this is a high frequency, and this is your low frequency, and this is your inversion, and this is your depletion. So it will invert around the y-axis. Sorry, it will invert around the x-axis, not y. Is this clear to everyone? Okay, so these are the main CV characteristics that we were not able to cover in the previous class. So this is the main thing. I mean, many interviews you will be asked that what is the difference between a low frequency and a high frequency characteristics. So let me now, what change that we see in the high frequencies, we were not able to generate the thermally generated electrons, right? And that's why the C depletion or the C inversion gets stuck to the C depletion, right? It did not go up as Cox. So what we do is, in the MOS cap, what we do is, so we, if you remember, we have this MOS cap. Let's say this is VB. This is, let's say I'm not making a complete gate. This is the oxide. This is a VG. So now this is the MOSFET that we already studied. So now the MOSFET, there is just one difference. We have a ample source of electrons around both left and right. So this is, let's say, P type. And what do? We add a source of electrons on both left and right. So what do you think will happen now even if we apply high frequency? So what do we require at the surface when we want to invert the let's say a MOS capacitor? We wanted a sheet of electrons, right? Is this clear? Whatever I'm asking? Yeah. So what I am saying is we were not able to have a sheet of electrons here, right? When we are applying higher frequency. So these electrons were not thermally generated because of the fast nature of the frequency. There was no response, or it was not fast enough to respond to the high frequency, right? In the high frequency characteristic of a mass capacitor, and that is why this CV remains like down. So now what do we have? We already have a source of electrons present. So we have a highly doped N plus region present, and this is what we call as source of electrons. So this region what we call as source, this region is what we call as drain, and this is the basic difference between a MOS capacitor and a MOSFET. So in a MOSFET, we have a source and a drain, and even if you apply higher frequency now, what will happen? We already have ample of amount of electrons. So these electrons will help in getting your charge inverted. So even at high frequency, your capacitance will go up. Are you able to understand this? So in a MOSFET, for both high and low frequency, your curve will look like this. So this is a very popular question that they ask in interview, that what is the difference between a high frequency or a low frequency curve of a MOSFET? So the answer should be there is no difference because we already have a source of electron. But in a MOS capacitor, there is a difference because we don't have the thermally generated electron, so it will go or it will remain down. If there is any doubt, please quickly ask. Any doubts here? Okay, great. So yeah, and in general, we make MOSFET in a schematic view as something like this. So for a NMOS cap, your current goes out from source. So since your electrons are going from source to drain, your current will go in the opposite direction, right? So we write drain to source current, and your electron flow is like this because we are applying a positive drain voltage. So this is a MOS capacitor symbol. So this is the gate, this is the drain, this is the source, and yeah, this is the drain to source current. So is the difference between a MOS capacitor and a MOSFET clear to everyone? Okay. So now we have always kept this body bias to zero, right? So let me quickly show you the effect of body bias. So why do we have, or why do we even require a body bias? So this concept is what we call as body voltage or body bias modulation. So we also have substrate bias. We sometimes call it substrate bias also because it is attached to the substrate. So yeah, now I'm doing everything with respect to a MOSFET. So this is, let's say, N plus N plus. This is a T-aux, this is a gate, this is a source, this is a drain, and this is a body. So now this is P-type. I'm still talking about NMOS FET. So now let's say I apply a positive bias at the body. So you see here it is a P-type and this is N-type. So can you tell if I apply a positive bias whether, so can you see that it is like a PN junction between a body and the source? You see? Yeah, so if I apply a positive bias, what will be the nature of the PN junction? If I, let's say, yeah, exactly. So if I apply a positive VB, that means if your VBS is greater than 0, then your PN junction will be forward bias. And similarly, if I apply a negative bias at the body, it will be reverse bias, right? That is obvious. So using this, by what we can do is we can play with your characteristics. So we know that the surface potential that was required to have the electrons was 2 phi f. But now using this body bias modulation, what we can have is we can achieve either a quicker inversion or a delayed inversion. So how do we do that? Let's say I apply a VBS which is negative, or I can write the same as VSB which is positive. That means source is applied a positive voltage. That means it is in reverse bias, right? So now since we have already applied some of the reverse bias, what will happen? What will happen? It will help in inversion, right? It will attract all the holes and it will make all the electrons go up. Are you all able to understand this? Let's say I apply a negative bias, the holes will be attracted here and your minority carriers will go up. It will help you in inversion, right? So your surface potential that was required as 2 phi f before, it will be now only minus VBS. Sorry, phi f. Or I can also write this as 2 phi f plus VSB. VBS and VSB are already interchanged. So your VT that was required before was VFB. So VFB there will be no change. Q depletion over C of plus phi s. So now phi s is equals to, as I have written, it is 2 phi f plus VSB. And in this also depletion region, if you remember your Q depletion was what? It was under root 2 phi s QNA into psi s. So now your psi s will be 2 phi f plus VSB. So this is what we call as body bias modulation. You can use your body voltage to either increase or decrease your threshold voltage, or to make it turn on slowly or fast. Is this concept also clear? Okay, that's great. So now we can say that we have comprehensively covered the MOS capacitor, the CV characteristics of a MOS capacitor, and also the CV characteristics of a MOSFET. So the basic difference between a MOSFET and a MOSCAP we have already covered. The CV we have now understood clearly, and also what we have seen is we have seen the effect of body bias on the MOSFET. So this is a comprehensive analysis of the complete week 6. Then now what we can do is we can quickly go towards the semi-classical transport theory questions, which is the first topic of this particular week. So the first question, let's do it by questions directly because it is easier to understand. It is similarly as we have the week 3 content. So it says in semi-classical transport, the electron in a cluster are represented as what? So anyone wants to take a guess or why? Yes, exactly. So we did study this, that electrons in a semi-classical transports are like particles, but with some effective mass. And they can also act like waves, but that was the case when we are using the quantum transport, the Schrodinger that we studied. So in semi-classical transport, it's always electron acts like a particle with some effective mass. So option B is the correct answer to this. Okay, now the next topic basically here is the Fermi-Dirac distribution function. So it says, how does an increase in the temperature affect the Fermi-Dirac distribution function? So do you guys remember what is Fermi-Dirac distribution function? Yeah, exactly. So Fermi-Dirac distribution function, the mathematical representation was something like 1 upon 1 plus exponential E minus EF over KT. So basically the Fermi-Dirac distribution function, it tells you, as you said, the probability of finding an electron at energy level E and at temperature T, right? And similarly, we can also calculate 1 minus Fe because it is probability. So it was probability of finding holes. So this we have already studied, so I'll not go very deep. And if you remember, we took three cases. The first case was that we have an EF in which we have a non-zero temperature, but your energy is equals to the Fermi Dirac. Oh, sorry, the Fermi level. So in this, what we were able to find is that we have 1 upon 1 plus exponential of 0, that is 1 by 2. So from here what we calculated is that Fermi energy level is that level at which the probability of finding an electron is, yeah, is always half. So from this we give the definition of Fermi level, that it is that level at which the probability of finding an electron is always half. So this we have already covered in week 3. You can go through that again if you want some more detailed version of it. And then we took two more cases, if you remember, in which we took only at 0 Kelvin. The first case was when the energy is greater than EF, and the second case was when energy is less than EF. So in this we calculated the Fermi Dirac. In this also we calculated the Fermi Dirac. So what was that? It was 1 upon 1 plus exponential of infinite. And this was 1 upon 1 plus exponential of. So this come out to be, yeah. And then from this we were able to make that graph of Fermi Dirac as a function of energy. Let's say this is your EF. So you are able to say that, as you have just calculated, that below Fermi it is always 1 and after Fermi it is always 0. And then what we did is we started to increase some temperature. So let's say now T is equals to non-zero Kelvin. So what happened to the curve? Because of the increase in temperature, we have some electrons going from conduction to valence, right? Valence to conduction, sorry. So we have some decrease in the Fermi level. So this is, let's say we disturbed at, this is at T1. And let's say I apply some more temperature. Okay, let me use some different color. That, so let's say this is my second curve, which was at T2. We already studied this. So which one is greater, T2 or T1? Yeah. So more the temperature you will apply, the more broader it becomes. Is this clear? So now the what was the question? Let me see. Yeah. So it says, how does an increase in temperature affect the Fermi Dirac distribution function? Okay, yeah, it becomes broader. That is true. So option B is the correct answer. Is this clear to everyone? Okay, let's move towards the next question. It says, what is the significance of introducing the quasi-Fermi levels? So anyone remember what is quasi-Fermi level? We covered that, I think, in diodes. So this is a very important concept, even if we have not covered. So quasi by itself in English means different Fermi levels. So if you remember, we started when we are studying the band diagrams. So we started with p junction at equilibrium, in which we made something like this, if you remember, in which the Fermi level was constant, right? When we were at equilibrium. So this was your phi p, your phi n, sorry, and this was your VBI, which was also this. So the VBI was phi p plus phi n. Do you remember this? Yeah. So what we did is then we studied about two cases, right? One was the forward bias and one was the reverse bias. So let's say when we applied the forward bias, what happened is the Fermi level will not align, right? Yeah, it will shift. So for P side, it shifted downwards. For N side, it shifted upwards. So now this was your, sorry, this was your phi P, this was a phi N, and this is your VBI now, which is also this. Sorry, this is not VBI now because VBI is this. Or what I can say is this is now the actual total voltage that is due to its changing. So VBI is always phi P plus phi N. So this is your V total now. So which we see, so the difference in these two voltages was actually VA, right? Let me make that will make it clear. So these two lines, if I extend, so this is actually VA. So these are the quasi Fermi levels. That means we have different Fermi levels, and whatever the change in the Fermi level is actually due to the applied voltage. So now, if you remember, we calculated V total as phi P plus phi N minus VA, which is nothing but VBI minus VA. Is this clear? I mean, I have already covered this in detail in the p-n junction lecture, but I was just trying to refresh the concept of the quasi Fermi. So if you have any doubt, let me ask quickly. Otherwise, we can move ahead. Okay, yeah, sure. So as I said, that in the p-n junction, what we started is we started with the equilibrium when we have a constant Fermi level. But as soon as we go out of equilibrium, that is, let's say we have applied some bias, there will be some change in the Fermi, right? Do you agree with this? That there will be a different Fermi level at the p side and there will be a different Fermi level at the n side? Because we have to have that change, whatever we are applying in terms of Fermi level. Is this part clear? So whatever that change will be your applied voltage is what I'm saying. So that is I'm denoting as VA. So having these two different Fermi levels is what we call as using the quasi Fermi level. Quasi means we have different Fermi levels. And then you already know that the difference between the EI to this whole shift in the curve is actually the total difference in the voltage. And your VBI was phi P plus phi N. So if you see clearly in this plot, okay, let me shade this. So if this is phi P, and let me use some different color. This is phi N. And now this is, okay, not this, maybe yellow. And this is your VA. So you can clearly see now, I think, that phi P plus phi N, and if you delete the VA from this or remove the VA from this, is actually the V total. So this was VBI, which was the case phi P plus phi N, and minus VA is the applied or the change in the Fermi level, that is a quasi Fermi level. Is this clear now? Hmm. Hmm. Yeah, V total is equals to VBI, right? Yeah, because we have a single Fermi level. But after applying the bias, we need to have different Fermi levels because it is no longer in equilibrium. That is why we are calling this as a concept of quasi Fermi level. Does it make, yeah? Does it make sense now? Uh, whosoever asks, does it make sense? Yeah. So now, okay, let's see the question. So it says, what is the significance of introducing the quasi-Fermi levels? So the first option is to simplify mathematical calculation. So this is wrong. We are not simplifying anything. The second question is to model the carrier concentration under non-equilibrium condition. So this is true, right? So at non-equilibrium only, we are having the quasi-Fermi level concentration. So option B is the correct answer. Let's read the other two options also. To increase the band gap of the semiconductor. Band gap never changes, right? Semiconductor, the band gap will always remain same. And then the third last option is to reduce the temperature dependency. So this is again wrong. We are not reducing or increasing. It's not related to temperature at all. It's related to the non-equilibrium condition. So option B is the correct answer. Is this clear? Okay. So let's move ahead to the next concept, which is I think the scattering and mobility part. Uh, so let me explain that too. I think so. The question is determine the average mobility. So we have two different mechanisms that we have in terms of mobility. So do you remember we studied again in the I think the week 3 a concept which is called as drift velocity, and the plot was looking something like this. Can anyone explain this plot? if you remember. Yeah, exactly. So, I mean, yeah, we started with Vd equals to mu e, and we understood that on the application of electric field, there will be some vibrations in the lattice, and due to which there will be some collisions, due to which what do we have? There is no constant acceleration. There will be a constant collision, so there will be some acceleration and deceleration, and there will be a time that your velocity will remain constant. There will be no acceleration as such, and that velocity, what we termed as, is called as the drift velocity, which is this Vd equals to mu e. But this will not happen like forever, because once we reach a electric field at which there is a lot of collisions, then your mobility actually degrades. So your electric field is increasing as your mobility is decreasing, and at that point your disk velocity becomes constant, and this is equals to your thermal velocity, right? If you remember, we calculated VTH as under root 3 kT by m something. Is this clear? So this was your linear region till the Vd equals to mu e was following that. As you apply the electric field, your disk velocity increases, and at a certain electric field, which is what we call as, let's say it was around some critical electric field, it was approximately 10 to the power 4 per centimeter, volt per centimeter, I mean. So we were able to find that we have reached the thermal velocity, and after that your velocity will never increase because your mobility is degrading. So this is degrading because of the scattering phenomena. Is this clear to everyone? Yeah, so there are two scattering phenomena that we need to understand. Let me quickly cover that because that is the last topic for this particular week. So the first comes from the lattice vibrations. So this is what we call as atomic vibrations also, because there are atoms in the lattice. So as you increase the temperature, so it is all related to temperature. What do you think will happen? Your vibration will increase or decrease? Yeah, if your vibration will increase, what do you think happens to your scattering? Yeah, if your scattering increase, what do you think will happen to your mobility? Yeah, because there will be more collisions. More the scattering, less higher will be the collisions, and your mobility will be low, right? So your lattice vibration, the relation is actually as the temperature increases, your mobility decreases. So this is a relation for the lattice vibration. Is this clear? Any doubts? Yeah. So the sec yeah, 3 by 2 comes from some mathematical relation. So I mean the whole point of me saying this is it is inversely proportional to temperature. This 3 by 2 comes from a very long derivation, so I don't want to go very deep in this. You just try to, sorry. Yeah, exactly. So minus clears that. That means it is inversely proportional to temperature. So this number actually comes from a very long derivation. I mean, the whole point of saying was as you increase the temperature, your mobility will decrease. Yeah. The second type of scattering that we have is due to impurity. Impurity scattering, or this is what we call as impurity. So now this depends upon, as it is the name suggests, on the impurity level. So let's say Ni is your impurity. So try to understand here as we increase the temperature again. So this depends upon the time it spends around the impurity. So as you just said, as temperature increases, so your scattering increases, right? Now I'm talking about your immobile ions that are not moving. So what do you think, if its scattering increases, will the electron spend more time around those electrons, or will it spend less time with those electrons? Or sorry, ions, not electrons. Yeah, it will spend less time. And what do you think will happen to the mobility if it is spending less time? Yeah, it will increase. So it basically depends upon two things now. It increases with temperature, and it also is a function of Ni because lesser will be the impurities, more will be the mobility, right? Is these two things clear to everyone? Please let me know if you have any doubts because these are the two main scattering phenomena that we need to study. Hmm. Yeah, barrier. Yeah, exactly. So hence your mobility will even increase more, right? So that is why I've written it is inversely proportional to your impurity, number of impurity ions. Make sense? Yeah. So we have definitely divided it into two things. One was due to lattice, or let's say one was due to impurity, which is this we have just written, which is mu I is proportional to T raised by 3 by 2 by Ni. The second one was lattice vibrations, which is nothing but inversely proportional to 3 by 2. So if I try to plot this, so what this is a very important plot. This is what we call as the mobility versus temperature plot. So since this is 3 by 2, 3 by 2, so I will plot log mu by log temperature to make it linear. So now, yeah, there is one more thing is because impurity scattering, lattice vibration takes place when it is lower, right? At very high temperature, what will happen? Your lattice vibrations will be more, right? So your lattice impurity or your lattice scattering will take place at high temperature, whereas at the lower temperature, your impurity scattering will be dominant. Is this clear? Because at high temperature, there will be more and more vibrations, and hence your mobility will degrade. Is this clear to all of you? This is again one more thing that I want to discuss, that your lattice scattering is more dominant at higher temperatures because more vibrations means lesser impurity. And at smaller temperature, this impurity scattering dominates. Any doubts? Sorry? Hmm. No, you need to understand that for the lattice impurity or the lattice scattering to dominate, you need to have very high temperature, right? Whatever you will do at high temperature, your mobility will degrade, right? But at lower temperature, what you see is there will be lesser lattice vibrations. And at smaller temperature too, there will be this impurity scattering only because it will increase as it will spend less time with the impurities. So the main concept you need to understand it that at higher temperature, you know your lattice vibration will dominate. So hence you have a decrease in the overall mobility at high temperature and increase in mobility at lower temperature. So yeah, if you try to plot the log version of this, so it will be linear here and it will be linear here because I'm plotting the log. This was proportional to 3 by 2, this was proportional to minus 3 by 2. So your actual plot looks something like the smoothened version of this. So this is a very important plot. They also ask this in a lot of interviews. So your 1 upon mu effective is actually 1 upon mu due to lattice plus 1 upon mu due to impurity. Is this clear to everyone? Any doubts? Sorry, I did not understand what you're saying. Can you repeat? Hmm. Yeah. So what is the question? Yeah, because it is like it is a series combination of these two, right? So either of this will dominate. I mean, if this dominates, then this is the dominating factor. If this dominates, then this is the dominating factor. So we need to have the one by of that. So this is what we call as the Mathesian formula or the Mathesian rule. So my point is whichever has a higher value needs to dominate. So that is why this formula comes out. So whatever the amount of scatterings that you have, I mean, I have in general written two because these are the two important mobility. So let's say even you have the third one, it will come out to be something like this: 1 by mu 1, 2, 3, 4, and so on. So this is a general formula, I mean. So the final plot will look something like this only. So this is, as I said, 3 by 2. This is minus 3 by 2. And your 1 by mu effective will be 1 by mu L plus 1 by mu I. Clear? So if this is clear, the question here said that determine the average velocity, sorry, mobility with two scattering mechanisms having mobility of this and this. So can you calculate this now? So let me also do it. So 1 by mu effective will be 1 by mu L plus 1 by mu I. So which is 1 by 300 plus 1 by 150. So mu effective will come out to be 300 into 150 plus 300 plus 150, right? Which is 3 times. So it will come out to be 100 centimeter square per volt second. Is this clear? Okay, let's quickly do one more problem. I think I do have that. Yeah, so this is one more problem. So it says if two scattering mechanisms have the same energy dependence in mobility this and mobility this, so the total mobility will be what? So can you quickly calculate and let me know the answer? Yeah, exactly. So it will be 0.125 times 0.125 plus 0.25. So it will come out to be 0.0833. So one thing you are able to notice, I think, so whatever will be the smaller value of these two, the answer will be smaller than that. In parallel, let's say you have, I mean, in general, let me give you some analogy. So let's say you have two resistance in parallel. So if R1 is greater than R2, so the final answer will be less than R2, right? I mean, I hope you are able to understand this. So similarly, so you can see the options directly. So 0.125 and 0.25. So the lower one is 0.125. So the answer should be lesser than 0.125. So this cannot be the answer, this cannot be the answer, this cannot be the answer. So the option is this. So you don't even need to calculate. Are you able to understand what I'm trying to say? Yeah. So yeah, let me go towards the top now. I mean, let me see if there are other things. So we studied in this particular week, we studied about the transport theory, which is electron. I mean, it is what's just in general that electron behaves like a particle with some effective mass. We study about the distribution function. Then we have some Boltzmann transport equation that I'll like to cover because it is a longer topic. So I'll start with this maybe in the next lecture. And RTS, so these two are interrelated. And then we've covered some scattering. So what are those two main type of scattering and mobility? And also in this lecture, we have covered the threshold voltage and trap charges question. That was the first question that we did. There were some trap charges also. The MOSFET that we have seen. What is the difference in the MOSCAP and MOSFET IV or CV characteristics? So IV, I will show you or I will discuss this once we have some more understanding. So I will also cover this topic and non-idealities that we have seen in the low and high frequencies. So I think we have done some comprehensive analysis for weeks 6 and 7. And now in the subsequent weeks, we have more or less more and more mathematics. So week 8 and 9 are both drift diffusion model. So in this, we will see how the actual mathematics come from and what is this drift diffusion mechanism. So yeah, I mean, for now, if you don't have any doubt, I think we can wrap up for today. So let me go through it again quickly. So we covered the most important concept of Morse gap, in which we covered each and every formula in a single problem. We calculated VFB, the depletion width, and the threshold voltage. Then we understood the difference between the low and high frequency CV characteristics, that how it always remains down for a higher frequency and how it goes up for the lower frequency. Then we did the MOSFET, that why it is always up in a MOSFET, because it already have a source of electron. It does not need to get it thermally generated, so it always remains up even at high and low frequency in a MOSFET. Then what is the role of body bias? And then some concept of semi-classical and the Fermi-Dirac distribution function. And at last we covered the quasi-Fermi and the mobility, or sorry, or the scattering. So is there any doubt in all of these things? Okay, so if not, I think we can wrap up the session for today and we can meet next week, same time. So yeah, let me stop the recording.